All right, AP Calc, here are some trig examples in which we're going to use chain rule. Number 29 from page 144. So on 29, if we're going to think in terms of composite functions, it's like sine is the outermost function. So if we did the whole f of x equals g of h of x business, it's sort of like the sine is the g and the x squared plus 2 is the h. We take the derivative of sine first. Okay? So the derivative of sine is cosine. Right. But when we take the derivative here, you got to remember that the h of x remains. So it still has x squared plus 2 inside. Now take the derivative of the inside. The derivative of x squared plus 2 is 2x. Now, instead of putting it times 2x over here, I'm just going to put the 2x out front because that's the traditional notation that it takes, and that's my final answer. The traditional notation is to put the variable expressions before the trig, okay? Now, the variable expression inside the parentheses is the angle that cosine is being applied to. So, variable expression, they represent two very different things. Yeah, 29 is pretty easy. What happens when we add a degree of difficulty? Now it's not just cosine of 3 theta, it's cosine to the 5th power of 3 theta. Well, I'm just going to do a quick rewrite to give us a better perspective on this. This is like the cosine of 3 theta to the 5th power, just keeping that in mind. And really now it's a 3-pronged function composition. The innermost is 3 theta, then we've got a cosine, then we've got an x to the 5th power. It's sort of like you're doing 3 different derivatives here if we look at it from the perspective of composite functions. So, I think all we got to do though is work outward and then move our way in, and we'll be fine. So the most outward function is blank to the 5th power. Think of it as theta to the 5th power. You'd bring the 5 down as power rule dictates. You rewrite everybody inside the brackets. You take 1 away from the power, and that takes care of your first outer derivative. Now, the inner derivative, we're talking cosine. The derivative of cosine is negative sine. We're talking cosine of 3 theta, so it's still negative sine of 3 theta. Derivative number 2 done. And now we work on our innermost function. The derivative of 3 theta, it's kind of like the derivative of 3x. It's just going to be 3. So now, the best way to tidy up this function and write it, like normal mathematicians would, is to say our constants go out front first. So 3 times a negative 1 times a 5 is negative 15. Our simplest trig function is sine of 3 theta. I'll put that next in line. And then cosine of 3 theta to the 4th power would be the last one. I'm going to rewrite it in the same notation that this one took and just call it cosine of 3 theta to the 4th power. And you know what? I should probably get in the habit of checking these answers, right? Because some of the videos have not gone well when I don't check my answers. So this was number 29 and 31. Let's make sure. 29 checks out. 31 also checks out. Actually, they put the cosine to the 4th left of that. They switched these around. I guess it doesn't really matter because of the commutative property. I'm going to keep it as is. So there's my first derivative. Let's check out 33 and 41. All right, so we're talking secant of 2z plus 1 to the 2 power. Now, this is different notation than that. We would have to have the 2 right by the secant to think of this as secant of 2z plus 1 times itself. It's just the angle that's being multiplied by itself. So here's what we do. We say the derivative is the outer function, secant first. So the derivative of secant is secant tangent of whatever angle is given to us at the beginning. So this is secant of 2z plus 1 squared times tangent of 2z plus 1 squared. Hopefully that makes sense to you guys. The derivative of secant is secant tangent. So I'm not rewriting this. It's literally, this is part of its derivative. Yeah. All right. I should be color coding these. Part 2 derivative. We take the derivative of 2z plus 1 squared. Looks like we got some chain rule action again. Bring the 2 down. Rewrite. Take 1 away from the power, and then multiply by the derivative of the inside. So our final answer is going to be 4 times 2z plus 1, and then multiplied by our secant tangent. Now be consistent. Make sure you don't just put secant and then a blank spot. It is the secant of 2z plus 1 squared. Tangent of 2z plus 1 squared. All right, number 41 is a little different. Wait, let's check it. Perfect. All right, number 41. It's z squared times the cotangent of 5z. So we've just added product rule to this mix. You guys should try this one on your own. Pause the video. All right, let's check it. See if you're right. We'll do rewrite in black, derivative in red. So the derivative of the function k is equal to the first times the derivative of the second. The derivative of cotangent is going to be negative cosecant squared. Of 5z. And then now we take the derivative of 5z. That's just 5. Awesome. Plus the second function times the derivative of the first. 2z. And that's pretty much the basics of this one. You're done. Except this is kind of iffy. Let's tidy it up. Negative 5z squared times the cosecant squared of 5z. That's the proper way to write it. Plus 2z cotangent of 5z. Awesome. All right, now, I will say this. Sometimes students will have a wrong idea about how trig works, and they'll say, well, can't we factor out a 5z? And the answer is no, you can't factor out the 5z because it's attached to the 5z is attached to the trig function right here. So you can't say that this one has a 5z and that one has a 5z, so factor them out. All right, I think this is the last one I'll do. Number 43. I think I need more horizontal space to make this happen, so I'm going to erase the stuff before it. Why don't you pause it and try it on your own, though? Number 43. All right, so it looks like we got product rule with chain rule nested in both parts. This might get ugly. All right, we are going to rewrite in black, derivative in red. So h prime of theta equals, my first function is tan squared theta, times my second function. All right, remember, this is like the secant of theta to the third power. So I'm going to bring the 3 down, multiply by secant. It's the whole thing to the 2 power. Maybe this will visually help you guys, but you can just write it here if you want to. That's fine. And then you take the derivative of the secant of theta, which is secant theta tangent theta. Plus the second, which is the secant cubed of theta, times the derivative of the first. Again, this is tan of theta squared. So you bring the 2 down, you rewrite tangent. It's to the 1 power now, and then you multiply by the derivative of tangent, which is secant squared. All right, can you guys see that? I think it's showing up okay. Yeah. All right, now, secant squared times secant would be secant cubed. Tangent times tangent squared is tangent cubed. So I can rewrite this as 3 secant cubed theta tangent cubed theta. And then the second part's going to be, wow, secant to the 5th power times 2 times tangent. Now, this might be a perfectly acceptable way to express the final answer, and that's what they do in the textbook. Recognize, though, that sometimes some exploration can prove to be fruitful. Like if we took out a secant cubed and a tangent, what's it look like? So I'm factoring out secant cubed, factoring out a tangent. That would give me this. And then over here, now, this doesn't lead me to any further simplification. I mean, technically, I can rewrite tangent in terms of secant if they're both squares, so I could use a pidenity here. And we could have hit the jackpot and gotten something like secant squared minus tangent squared, which would have reduced everything down to 1. But in this particular case, nothing special seems to be happening. So you could probably have stopped on that previous line. All right, I hope these examples are helpful and enlightening, and you enjoyed watching the video. Thanks for watching.